Okay, in this video we need to talk about the idea of molarity, which is the most common unit of concentration, which is a measure of how much material is dissolved into a solution. So I need to define a few things before we even get to molarity. First of all, we need to talk about the idea of solutions. And they are made of two components. There is the solute. This is the material being dissolved. So for example, if you had salt water, this would be the salt. Then there is the solvent. This is the material that dissolves the solute. So if you did salt water, the example here would be water. For almost everything we're going to do in Chem 1 or Chem 2, the solvent is almost always water. And if you ever make it to like organic chemistry, I promise there are thousands of solvents as options. Right now we're just going to focus on water. If you have a solute dissolved in a solvent, that is a solution. Okay. What we care about for this section of the chapter is trying to put some numbers with this to figure out how much solute there is in a solution. Okay, so molarity, which I guess I'll rewrite down here, is abbreviated as a capital M. M is way too popular of a letter for abbreviations in chemistry, so molarity must be really, really important if it gets an M. I'll just tell you right now. Anytime we're dealing with concentrations, there are multiple ways to do this. Molarity is the most common option. Molarity is equal to moles of solute per liter of solution. So the moles of solute, we know how to convert from grams to moles, stuff like that. You just solve for moles of just the solute part, and then you divide it by the total volume of the solution. Typically, the solvent is most of the solution, so the total volume of the solvent and the total volume of the solution will be similar, but the solute does have volume, so we need the total volume of the whole thing all together. Typically, these are made in something called volumetric flasks. They have a little stopper at the top, and they have a little line right there. What you do is you put your solid in there. I guess we'll make it blue, whatever. You measure out your solid, so you'll know its mass. You'll be able to convert to moles using the periodic table like we've done before. Then you fill this about halfway with water. Okay, I'm just kind of doing it like that for right now. Then you swirl it around until all of it dissolves, and then you fill it up to this line. On this line, it should form this thing called a meniscus. It's a little curve where the bottom of the line, or the bottom of the curve, is right on sitting on that line. Okay. And this is a set value for volumetric flask. Let's say it's a 100 milliliter flask. Usually you get 2 decimals of accuracy on this. So you can get 5 sig figs. You can very, very accurately measure this total volume, which allows you to accurately measure a molarity. Okay, so this is the setup of how we do it. For right now, let's just try an example to see how the calculations are done. In a lab setting, this will probably be super useful also. Okay. Yeah, so I guess I should point out, when we used molar masses, like these little grams per mole values, we can visualize that as our conversion factor between moles and mass and moles and mass. This is our conversion factor between moles and volume. Okay, so anytime you have volumes in the story, you're probably going to need molarities. Okay. So we want to know, what is the molarity of a 125.0 milliliter solution with 7.50 grams of, I don't know, I guess I probably should pick a salt here, magnesium chloride dissolved. Okay. So, essentially what we're trying to do is we're trying to make it have these units. We want moles of solute on top and liters of solution on bottom. So this number needs to be converted to liters, and this number needs to be converted to moles. This will need to be on top and that will need to be on bottom. So I'm just gonna write it like this. Okay, so we have 7.50 grams of MgCl2 divided by 125.0 milliliters. Like I just got done writing, I guess I'll write it again just for clarity's sake. This needs to be converted to moles, which we know how to convert from grams to moles, periodic table, we've done that before. This needs to be converted to liters. That's literally just a basic unit conversion. So, first thing we do is we look up magnesium and chlorine. For the sake of sig figs, I'm gonna make sure I have at least 3 decimals here. So magnesium is 24.305 plus MgCl2, so 2 times the mass of chlorine. 2 times 35.453. Okay. Comes out to 95.211. Grams per mole of MgCl2. So our grams will cancel out and we'll have moles of MgCl2, which is what we're looking for. MgCl2 is our solute because it's the thing being dissolved, so we want moles of that on top, so we're halfway there. Converting from milliliters to liters, basically there is 1,000 milliliters in a liter. Milliliters canceled out. We will have moles per liter, so we must have done it right. So what we're gonna do is we're gonna take 7.50, help if I get it the right numbers, sorry, divided by 125.0, hit enter, divided by 95.211, hit enter, times 1,000, hit enter. And the answer comes out to 0.6, I guess 3 sig figs, 0.630. At this point, you can leave it as moles per liter, or you can just write it as capital M. I will tell you in a lab setting, most people write it as capital M, so I'm just gonna probably start getting in the habit of doing it that way. But this tells us that the solution, every liter of this will have 0.630 moles of magnesium in it. Okay? Not too bad, right? Let's try a slightly harder variation on the same type of problem. We want to know how many grams of, I don't know, I guess I probably should pick another compound. Iron acetate, iron 2 acetate would be needed to make 200 milliliters of 0.435 molar iron 2 acetate solution. Okay, so I am going to visualize this in terms of units here. I'm going to visualize this as 0.435 moles are in 1 liter. It's our conversion factor between moles and volume. Yes, this has sig figs, and yes, we need to worry about it because it is a measured value, but we can pretend like it's a unit conversion and treat it as such. So what we have is 200 milliliters. That's our final volume. This is in moles per liter, so we need this in liters. So we're going to divide by 1,000. Okay, milliliters cancels out. And then I need liters to cancel out. So this side will go on the bottom, this side will go on top. Okay, liters will cancel out. And now we have moles of this compound. The next thing we need to do is convert this from moles to grams. Anytime we're converting from moles to grams, we use the periodic table. So, let's see if I can make this all fit on the screen. So, iron has a value of 55.845 plus, there is 2 carbons in the parentheses and a 2 times there, so 4 times the value of carbon, which is 12.011, plus 3 times 2 would be 6 hydrogens, which is 1.008, plus there's 2 oxygens in the parentheses, times 2 would be 4 times 15.999, which is the value for oxygen. Okay, plug all that in, we get a pretty big number, which is fine, and we get 173.933. we're going to multiply, oops, 933, not 993 grams per mole. We need moles to cancel out, so the moles will go on the bottom. Everything will cancel out, just like any other unit conversion, and we end up with grams at the end, which is the units we were looking for. Okay, so I'm going to very carefully type all this in. So 200 divided by 1,000, hit equals, times 0.435, hit equals, times 173.933, hit equals. And the answer is 15.1. I guess this has 3 sig figs, so 15.1 grams. So essentially what you would do is you would have a 200 milliliter volumetric flask. You'd measure out 15.1 grams of this, pour it in there, pour in a little bit of water, swirl it around until it dissolves, and then fill it up to the line where it's exactly 200. And your final concentration would be 0.435. Okay? All right, so there's a couple examples of how molarity works. Let's talk about something called dilution. Dilutions come up in lab situations quite a bit. Okay, so a dilution is the idea of you increase the total volume by adding solvent. To decrease the concentration or decrease the molarity. Okay, the equation is really, really easy. So M1 V1 equals M2 V2. I guess I could label a couple things here so you know what everything is. M1 is the initial molarity. So it's in moles per liter. That pen is dying, but I have another one. This is the initial volume. And M2 is the final molarity. And this is the final volume. Okay, but the equation itself is pretty easy most of the time. You will have 3 of the 4 variables. You just solve for the one you don't know. So let's try an example just to see how it works. So let's say we took this final solution that we made up here, 0.435. And we want to know how many milliliters of 0.435 molar FeCH3COO2 would be needed to make 500 milliliters. Actually, let's make that 100. Let's go with a smaller volume. 100 milliliters of 0.0655 molar solution. Okay, so we're going from a higher concentration to a lower concentration, and we have a final volume of 100. So literally, we just use this equation. What I'm going to recommend you do is just write M1, V1, M2, V2, and see what you know and what you don't know. It really doesn't matter which one's initial and which one's final, as long as you're consistent. But okay, so how many milliliters of 0.435 molar? That is our initial concentration, 0.435 molar. How many milliliters? We want to know this volume. That's the one we don't know. M2 is the final concentration, which is 0.0655, which is a lower number, which makes sense because we're diluting it. And the final volume is 100 milliliters. So the idea is we made 200 milliliters of this solution up here. We don't need all of it to dilute this down. We just want to know how many milliliters of this stock solution will we need to make this. So in terms of our algebra here, we are solving for V1, so we're going to divide M1 off of both sides. Whatever we do to one side, we have to do to the other. It'll cancel out over here, which means we get that. So V1 is M2 V2 times M1. So M2 is 0.0655. V2 is 100. and M1 is 0.435. Okay, I will point out that this is in moles per liter, molarity, and so you could convert this to liters, but honestly, the molarities are going to cancel out. So whatever units you start with for this, as long as your volume units are consistent, you could do this in gallons and it wouldn't mess anything up. Okay, but your molarities will cancel out, and when you plug everything in, you take 0.0655 times 100, hit equals, divided by 0.435. And by pure random coincidence, I got 15.1 again, but that's okay. It's weird when that happens. Sorry, 15.1 milliliters. So what you would do is you would take 15.1 milliliters of this stock solution up here, which has a concentration of 0.435. You would put it into a volumetric flask, and then you would fill it up to 100 with whatever the solvent is, probably water, and then your final concentration would be 0.0655. Okay, thank you.